I work for BlazingSQL right now. BlazingSQL is a pretty much a platform or a framework, if you will, for managing data or using GPUs, using your graphics cards. So we kind of take the advantage of this extensive parallelism of graphics cards to manage on the data much quicker than you do that on your normal computer. In terms of introduction, I worked for Microsoft for 5 years, and before that, I did my PhD in operations research, which is a part of applied mathematics, curriculum at the University of New South Wales in Australia. And yeah, that's pretty much in terms of introductions. In terms of how we understand how the AI works, I think I like to start always with defining what the AI is. Everybody keeps, saying AI. Everybody, we've heard, machine learning. We've heard data analysis. We've heard statistics. We've heard, lots of terms. So I would like to start with just kind of defining these terms, the way I understand them, and then the way to kind of like delineate how these multiple of, I sometimes call them buzzwords, placed together within the whole landscape. And then we are going to move on to talk about where do we find AI. People and great speakers before me have already mentioned that you can see AI pretty much everywhere. Whatever you do these days, AI is there. And I'm going to kind of give you some feeling for that, how where you find these, and then how we actually do it. So how we as data and scientists, as machine learning engineers, as AI practitioners, how do we actually build these models? Where do we start? What is the life cycle, and how what is the kind of process end to end to really build something that can be used by broader mass of people. So let's start with saying kind of people tend to use artificial intelligence, the term artificial intelligence and machine learning somewhat interchangeably. So you can see people kind of switch the context, and they say in one sentence AI, and in the next sentence they might be pondering on machine learning. So the question for me is that, is it the same thing, or do I really actually need both of these terms? Can I just use artificial intelligence all the time, or is really machine learning something different? When I hear machine learning, should I think something different than artificial intelligence? So for me, and it is kind of a broader understanding. Artificial intelligence is this aim. It's the aim is to make machines perform human-like tasks. So like self-driving cars, like flying helicopters on Mars, or driving the rovers on Mars. Or there's a bunch of other examples where you can think like AI is actually really performing a human-like exercise. And you might be, when you read, news on the internet, when you scroll through Twitter feeds, when you, read some other, data science related news, you might see that, robots from Boston, that they actually walk by themselves autonomously. So for me, the artificial intelligence is this kind of, a term that describes an autonomous system, something that can perform a human-like, task, like the one shown on the right. On the other hand, machine learning is something that is a subset of artificial intelligence. So I like to think about machine learning as a building block of artificial intelligence. And I will actually lift the lid a little bit more about this in a second. But machine learning for me is actually training the machine to perform a task without explicitly stating all the rules of the task that needs to be done. So in this case, of course, a computer scientist could write a program with all the conditional statements that if you see a ball approaching at you, move towards it so you can bounce it back. Machine learning would actually take the same exercise and then learn how to actually how to react appropriately when the ball approaches the paddle. So that's the distinction between machine learning and AI. And both of these areas of science, I want to say, they have a deep rootings in statistics. And statistics, is I want to think that it's definitely a broader field of artificial intelligence because it's lays down the foundations for all the models that we build. What I mean by this, whenever you build a machine learning model, whenever you build a regression model that I'm going to talk about, in a second, or classification model, what you really try to do is to find this, how, given all that I know about this phenomenon, what can I expect is going to happen? And that's fundamentally the domain of statistics and how statistics plays an important role in the whole, broad artificial intelligence area. So with that out of the way, and previous speakers, they had brilliant examples of fantastic usage of AI and machine learning, but AI is everywhere these days. So let me give you some examples. Some of these might be already very, very familiar to you. Some of these might not, but let's go through some. Whenever you go to eBay or Amazon, or you search something on Bing or Google or DuckDuckGo or whatnot, whatever the phrases you put in, there's model that runs behind that tells you that, okay, well, people that actually search for this word, they looked at these pages. That's the domain of search engines. Or when they bought a lantern, they also considered buying a torchlight and some headlights. Or people that bought some classical music by Chopin, they also considered they also bought Beethoven, and so on and so forth. So one of the morals that runs behind the scenes when you arrive on Amazon or eBay or whatnot, whenever you type your search query, there's a model behind that analyzes the previous purchases of people that are like you, that search for a similar term that you just searched, and they will give you recommendations that you might be interested in. So that's one of the, we call them recommendations models. Another thing that you probably use, maybe not day to day, but probably quite frequently, is that when you travel somewhere and you don't know how to get there, there is a machine learning model that actually analyzes graphs. So every single map you see, see on the screen right now, it can be represented as a graph of nodes and edges between those nodes that allows you to traverse that graph. And whenever you say, okay, I want to go from point A to point B, the algorithm behind the scenes, we call the algorithm is actually called single shortest path, tries to find the single shortest path between these 2 points by traversing the graph. Of course, as you can see on the right top hand side, you can have multiple ways of getting there, and then the objective functions is do you want to get there the fastest? Do you want to get there, in the shortest amount, the shortest distance? And then you can define whatever your preference is. You want to get there the fastest, or not burn as much fuel and then go there, a little bit slower, but a shorter distance. So that's another example of how AI encroaches on your life every single day. In terms of, in the field of healthcare, we see more and more, companies and startups showing up, and they help, physicians to detect skin cancer or breast cancer. When you think about, going to a doctor, going to a physician and having an MRI scan or having, a CT scan or whatnot, the amount of, these tests done daily and the amount of people that are actually qualified to analyze those images is so small, that the number of people that actually analyze the images is so small versus the amount of these images taken every day so large, that every single physician, every single radiographer, I think is the name for the person that actually analyzes those images, they only have 10 seconds to scan through the image and provide a recommendation that this is a simple skin tag, or this is actually a skin cancer. with AI, with machine learning models, with the new technologies that we have in place, AI can help with and then analyze these images at speeds that are not achievable by the current infrastructure, the current manpower. Another way of looking at AI, looking at machine learning models is if you look out the window, you can roughly say, is it going to rain in the next hour or not? So the weather forecast systems, they actually look further ahead, of course, and then try to predict the temperature, whether it's going to rain, is it going to be foggy, and what is the likely way that the path of the high pressure areas are going to move through the low pressure areas, and they might cause rain or they might cause snowfall, and we can some of these information, we can plan ahead and then decide whether we need to close schools because there's an inclement weather coming in, or we want to preserve, like in Texas right now, preserve some electricity because there's a huge heat wave coming, and some of the power plants are not necessarily performing at the full capacity. So all of these, examples of machine learning models that I presented to you here are effectively fall into two categories: the way we train with supervision or without supervision. There's a third category that artificial intelligence kind of developed, and it is a closer way of how we learn as humans. So when you actually, go and try different things and you fail and then try again, and then that process repeats, that's how we learn. And then the field of reinforcement learning, or the way that machines learn, called reinforcement learning, allows the machines to actually, perform these tasks, try and try again. Now you see on the screen hundreds, right? Or probably not hundreds, but tens of different robots that actually interact with some physical, objects in a simulation. Why this is running in a simulation? Because sometimes prohibitively expensive to actually build so many robots and train them, right? In the real world, right? Without really, knowing what they're gonna do. Sometimes it's actually, very, very dangerous to deploy something that interacts in the real world that is not trained yet. So before these models actually, get deployed to a physical world, you run them in so-called gyms. This is an example of the Isaac gym this is a virtual environment developed at NVIDIA that allows people and allows data scientists and machine learning engineers to actually train those robots in a virtual world where they can scale out to hundreds, if not thousands, of robots like this in order to teach them much faster. So then later on, when you have the model, you can deploy that to a physical robot over here, and not waste time, and also do not risk injuring anybody in the process. So I'm going to play a very, very short video for you over here that actually really shows the robot that you saw being trained in the gym and in the virtual environment before, already deployed in the real world.
In this lab, we want to develop robots that can interact with people in a natural way. So these robots need to be able to operate on very different tasks. It needs to be very easy to tell them what they should be doing. And also they should be able to do this in very different environments. In this demo, the Leonardo robot performs a reasonably simple block stacking task where it detects the different kinds of blocks, their colors, and then decides on which block it wants to stack on top of each other. We were able to train and develop the robot in simulation. We were using the Isaac simulation environment in which we were able to test our algorithms, to fine-tune control algorithms. As a result, the robot moves in a very fluent way. Also, we were able to train even the visual perception algorithms. The whole idea of using simulation environments only works if the simulation is accurate enough to really reflect what's going on in the real physical world. You need to have the simulation such that it can simulate how the robot manipulator moves if you send certain control commands to it. It needs to also simulate how objects move when the robot, for example, touches them. So the physics have to be right. And at the same time, all of this has to be done in a photorealistic way, because we're also using the synthetically generated image data to train our perception algorithm. And for that, we're using real-time ray tracing capabilities such that the objects have the right kind of reflections. We can change the lighting conditions, and all of this looks really the same way as it would look like in the real world, which makes it possible for the deep networks that we train on them to also be applicable readily in the real environment. Isaac Sim is going to drastically change how we're developing this next generation of robots. Rather than having to program everything by hand and testing everything on the real hardware, which can be very expensive, time-consuming, and even dangerous, we can then do all these tasks in the simulation, which will provide the experience that these robots need to make in order to learn to perform all this complex tasks so much faster and also easier.
Okay, so I hope this was heard right now. So what Dieter was talking here about, effectively, he touched upon pretty much what I was trying to land. Using the ISAC, the virtual environment, allows them to much more quickly develop these models, train these models, so then they can move those pre-trained models and then finalize the training in the real world without making the mistakes that can be, one, costly and dangerous in certain points. So if you look actually at the next example, imagine if you were to take an untrained model that tries to self-drive the car and then just let it ride on the streets. Obviously, that will be super dangerous for for everybody involved and other members of the traffic. So therefore, NVIDIA. I have some examples you can go and watch. How you can actually use that kind of gym to pre-train those models, to allow those models to train to the point where you can be confident enough to actually deploy them in a physical world and then still under monitoring drive the car around to fine-tune those interactions with the real world. A good thing about ISAC Sim, the simulation tool, is that what Dieter was also alluding to, with the new capabilities of nowadays graphical processing units, graphics cards, you can actually do ray tracing. So all of those reflections in puddles on the road, or the windshields of other cars that blind the sensors, can also be simulated to kind of find present those edge cases to the AI being under development, so it can learn how to react in situations like that. There's a bunch of examples that you can probably relate to. You've most likely used some of them in the past. Maybe you have a car that can self-drive and so on and so forth. So let's now talk about another example where you kind of interact with this in a very, very black box way. So you talk to Siri, Google, or Alexa, or other intelligent speakers these days. It goes somewhere, and there's a bunch of models that run in somewhere else in the cloud, most likely, where they do speech to text translation. So whatever you talk to Siri or Google or Alexa, it gets transcribed into some form of a text that then gets to, there's another model that tries to understand what you said from the context, the recent context or a general context, and then tries to find the right thing that you asked the tool to do, and then finally interact back with you, right? So, it can tell you a joke or, do something else that tell you the weather. So there's a bunch of interesting, applications that you touch, every day these days. So how do we do this? How does it work actually? So Archana and then the previous speakers, that they did a brilliant job about laying that foundation for us. So I'm going to try to give you a little bit higher level, but also still a little bit closer to how we as data scientists or machine learning engineers work every day. It all starts with data. So everybody was talking about data. We saw great examples of how the Vision app recognized the bills, how the data was collected, how it was artificially tainted in order to simulate those different examples, different situations that you can see banknotes in. So it all starts with data. We collect the data, and then it goes to model training. So once we train the model, depending on the question you ask, you can train a regression model, classification model. There's a plethora of different models that you can, that are at your disposal, that actually answer different questions, based on what you're really after. And then based on, I have a bunch of, this feedback, arrows that go back and forth. If you train the model and the model doesn't perform that well, you need to go back either to the data collection, or you need to go and then train the model with different parameters. So it can perform better, and then it will achieve the level of confidence that you want to have before you actually go and deploy it. And then once you deploy it, you need to monitor, and then if the model over time deteriorates, you go back to the drawing board, either by collecting more data or doing the retraining the model. So let's start with what comes first. The data comes first. So we collect the data. The data, Archana mentioned that she works with data sets upwards of hundreds of millions of records. The data is everywhere. And then by 2025, I believe that we're going to be generating as much data in an hour as we were, generating in pretty much a week in 2015. So that the amount of the sea of data or ocean of data that we see every day accelerates. And this is, any type of data. We collect numbers, we collect dates, we have, text data, imagery, videos, and, also sensory data from farm robots and so on and so forth. So the data is huge, and this is the first step. So we need to collect that. We need to store that data somewhere and learn how to deal with it. So the second step is actually kind of getting to that point, to getting familiar with the data. You need to look, if the data is clean. Do we have a malfunctioning sensor? Do we have repetitive, text in our data? Is it the right thing to be there or not? So in order to use the data to train a model, we need to do what we call a data cleansing. We find the missing values. If the sensor is malfunctioning, we're going to have missing observations, or the observations that are so out of scope that we call them outliers. To give you an example, I have a air filter system, at home, and recently one speck of the dust that got into the sensor, and then the sensor was suddenly, telling me that my air inside the house was kind of, reminiscent of being on the surface of the sun with, 1,000 particles of, CO2 per 1 cubic centimeter. So, which would be completely nonsensical if you think about it. But if we collect that data, we don't have that context. So we need to look at the data in order to detect these, outliers, missing values, duplicated observations that really will, when you build a model based on the data that is not clean, it will most likely render a model that is not really usable. And then we move to featureizing. So featureizing helps you to find, different, take the features, take the data that you have, and then convert it slightly into something else. Derive, sometimes it's very useful if you have a, if your data and the underlying the data grows exponentially. If you take a logarithm of that, it will kind of make it linear. And that way, it's much easier for any model to interact with such data. So the featureizing step helps you to find the better relationships between your data and the ground truth. The ground truth here I'm using in quotes, and for the reason that I already touched upon it a little bit, but there's technically three types of how you can train a machine learning or AI model. It's with a teacher. This is pretty much how we how we learn. So we call it a supervised learning paradigm, where you give the model an example, and it tries to learn it tries to explain it. The model tries to learn how to explain it given the data that it has. The second one is called unsupervised learning, or without the teacher, where we try, given that we don't know what the ground truth is, we try to find some patterns. And the final one you actually saw a little bit already when I showed you the video. It's a trial and error. So this is called reinforcement learning, where you let the robot learn by itself, but you provide this definition of what the success and all failure looks like. Okay, so I'm gonna go to Ashana mentioned about regression models and classification models. Regression models, they try to predict the actual value of certain function. Classification models, so in this particular case, an estimated price of the house. In the classification context, you try to figure out whether it's going to rain in the next 7 days. So or is the house going to sell in the next 7 days? So we try to provide a probability of something happening. When it comes to deep learning, pretty much the sky is the limit. So you can start detecting birds. You can start, predicting, predicting whether the car in front of you is going to stop or not. And the final, pretty much this is the final point. Training, because we have so much data, it can be taking a long time. For simple models that normally don't require that much data, it can be done in seconds. But when you, on the other side, when you look about the deep learning models, these deep learning models, they normally need to update upwards of hundreds of millions of parameters, and they require lots of data to actually train those parameters. These types of models, they can take days, if not weeks, to train. This is the final step from the life cycle. So when we deploy the model, we have a test in place that actually allows us to figure out how well the model generalizes, and then we have the kind of a continuous monitoring and the retraining if necessary, if the model deteriorates over time. And I think that's it. So in summary, I try to kind of draw the parallels between the artificial intelligence, machine learning, and how statistics plays role in this whole context. I showed you some applications. So we went through recommendations to self-driving cars, and then I hope that some of them were actually something that you've used in the past. And then I very quickly try to show you the life cycle and step by step how to build a model. And now I will definitely be open to some questions.
Awesome. Many thanks, Tom. So what an amazing, insight, the whole insight and how we went behind the scenes. So it was great. So a couple of questions for you, okay?
Mm-hmm.
So first of all, how can we avoid traffic crimes using AI?
Traffic crimes, you train a model. So ultimately, it's people that actually, drive in those cars, right? So you cannot really, you can have some places, some guardrails in place that don't allow you to go beyond, do something crazy. So for instance, if you drive with one of the newer cars, you might have some sort of a self-driving capabilities. And most of these cars, they are not autonomous driving yet. So every single time, there's a camera most likely in the car that will, scan your, whether you, texting on your phone or looking around, not paying attention to what's in front of you. And it will alert you, or will just disengage the self-driving system and hold the car, to a stop. Of course, in that particular case, if you are driving on a freeway, the car will most likely will try to get to the side. If you're not paying attention, get to the side of the road and stop on the side of the road instead of just stopping in place. But there's some some of the models that are under the guardrails that are already in place that allow you to kind of safeguard some of these models against an irresponsible, I would say, usage.
Fantastic. And I know there are a couple of more questions for you on the chat window. You're welcome to answer those. And with that, I just want to thank you for what an amazing talk today and going behind the scenes to explain how AI actually works. So thank you so much, Tom, and you're welcome to answer the questions on chat. Many, many
Pleasure
thanks.
to have been here. Thank you for having me.